Well, good morning, good afternoon, good evening, and welcome back to the last week of classes. So I cannot believe that this is it, or rather soon it will be it. Well, all right. So without further ado, let us start. Note before I start. This is actually the last. The last standard format class. On Friday, we'll have student presentations. So basically, I'll not be talking much on Friday. All right. Okay, so for today, the plan is to talk more about ultra powers and the asymptotic sequence algebras, also known as reduced powers among logicians. So the plan is basically to present one classical, very important theorem due to many hands that is one of the standard tools in classification of cyst algebras and von Neumann algebras. Throughout the lecture, U will stand for non-principal ultrafilter natural numbers. And as always, A will be a cyst algebra. Okay, and just to remind you, so if U is this ultrafilter, then by A sub U, we denote the quotient L infinity of A modulo Cu of A, the norm ultra power. Let me just remind you what Cu of A is. It is all sequences A in L infinity. Okay, so actually it wasn't notation. All sequences AN in L infinity, such that the limit as N approaches to the ultrafilter, so along the ultrafilter, this sequence, the norms converge to zero. So that's the norm ultra power, and A infinity is quotient of L infinity of A, and C0 of A. C0 of A is just sequences which converge to zero in norm. That's the asymptotic sequence algebra, or reduced product associated to Frechet ideal, as logicians would say. So here's the theory that I want to, whose proof, basically main ideas from the sketch of its proof I would like to present. It's not so easy to create it properly. Basically, ideas come from Duza, McDuff, and Alain-Pons in case of 2-1 factors. Then Efros and Rosenberg really stated, reformulated this for these algebras, and there were some minor additions later on. But here is, this is not the full theorem. This is just basically the easiest non-trivial instance of the theorem, which is already good enough. Basically, improving this, we'll see all the main ideas in the proof. So for every unital separable cyst algebra A, we have 4 equivalent conditions. All embeddings here are unital embeddings. First is that A absorbs the Carr algebra tensorially. Just to remind you, M2 to infinity is just the tensor product of countably many copies of 2x2 matrices. This is arguably in some sense, the most important cyst algebra, in the sense that it is highly non-trivial, and by a result of Gleam, you can find it everywhere, unless your cyst algebra is trivial. In some other senses, other cyst algebras are most important, so don't put too much weight on this. It's just that I like it. It's very useful as an example. Anyway, so number 1 is A absorbs the Carr algebra tensorially. Number 2, if we embed A into its tensor product with M2 to infinity, but by just basically sending A to tensor product with the unit, then this is an elementary embedding. I'll remind you what it is once we come to that, in case you forgot. I hope you haven't forgotten. 3, the Carr algebra embeds into relative commutant of A inside the ultra power, right? So remember, we take ultra power, we embed A diagonal into the ultra power, and look at everything that commutes with it. It is a massive C-star algebra. It is quantifier-free saturated. And the question is, okay, so does this embed unital into that? And 4 is the same, but M2 to infinity embeds into relative commutant of A in its asymptotic sequence algebra. Now, all right, so these 4 equivalent, but there are more equivalent conditions. So we can add the following. A is elementary submodel of A tensor M2 of C. Now, this A tensor M2 of C is really just 2 by 2 matrices over elements of A. And if you think of it that way, then this embedding is really A goes to diagonal matrix A00 A. So this is an elementary embedding. Second, 2 by 2 matrices embed into relative commutant of A in the ultra power, and same for the asymptotic sequence algebra. You may notice that this here is missing, right? So there is one fewer equivalence, and indeed there are counterexamples. If you don't know what Kirchberg algebra is never mind. Basically, there are some classifiable, nice, separable, simple unital C-star algebras that satisfy this. They absorb M2 tensorially, but isomorphism is not that nice. So you don't have the other equivalences. All right. So basically, what I plan to do is prove selected implications of this theorem. Actually started as selected implications, but at the end of the day, I'm actually going to say something about each of the non-trivial implications. All right, so let's get started. So yeah. Okay, so first let's start with perhaps the easiest one. Proof that if A is elementary submodel of A tensor M2 to infinity, then M2 to infinity embeds into the ultra power. Well, this is just something that we've seen before, basically just putting things together. You see we have A embeds diagonally into its ultra power. A also embeds into A tensor M2 to infinity. Now, this doesn't require any special assumptions, but we are assuming that this is an elementary embedding. This is separable C-star algebra. This one here is countably saturated. Right, so this is one of the 2 defining properties of ultra powers. And as we saw before, countably saturated C-star algebras are separably universal. If you have elementary embedding of one C-star algebra separable into it, and the embedding of that separable algebra into this, then you can just complete the diagram. Now, if you complete the diagram, then this copy of M2 to infinity, this 1A tensor M2 to infinity, it has to go into the relative commutant of A. And that's exactly what this is asserting, that M2 to infinity goes there. I would just like to point out to a small wrinkle here. You see, I'm just writing A tensor M2 to infinity. C-star algebraists know that tensor products are a very subtle operation when you talk about C-star algebras, because in many situations this is not uniquely defined. However, for the car algebra, it is uniquely defined. This C-star algebra is what is called nuclear. Actually, for car algebra, it can be proved by bare hands. But never mind. Basically, the point is that you see just the fact that M2 to infinity embeds into relative commutant, that this here is equivalent to that A tensor M2 to infinity embeds into here, and moreover, A goes into diagonal copy of A. This is a non-trivial fact which depends on these algebras that we have. That a tensor product is uniquely defined, and also that both algebras are simple, because you see for abelian C-star algebras, if something embeds into relative commutant, then those 2 algebras can generate something that is just a quotient of the tensor product. So basically, two unital copies commuting just means that this algebra generated by them is quotient of the maximal tensor product. Now, because both algebras are simple, it's not a quotient, and because one of them is nuclear, it is minimal tensor product. Right. So basically, in short, all you need to say is that alpha power is countably saturated and A is elementary submodel, end of the story. And everything is separable. Okay, so now we have the other similar statement, same assumption. A is an elementary submodel of A tensor the Car algebra, but this time we want to prove that Car algebra embeds into relative commutant in the asymptotic sequence algebra. Now this is different. This is different because, okay, first similar thing is that A infinity is countably saturated. So good. But so far so good. But on the other hand, A is not an elementary submodel of A infinity, except in some very, very exceptional cases. However, there is a sufficient amount of elementarity that is preserved for the proof to go through. I am not going to go over it. I'm just mentioning this because basically as a reminder that even if something doesn't go through in the obvious way, it may be quite often that there is a non-obvious way that if you actually remember how things are proved, that you can recover a proof out of that. So all that one needs to do is to see basically how what sentences are preserved in the operation of taking this cells apart. Let me know if there are any questions. All right. Now, next, we are going to, you see, so far, actually, I should say this, so far in these proofs, we haven't used anything special except that algebra was nuclear and simple. Right, so we need nuclearity to make sense out of tensor product, and simple for that embedding thing. Now we'll go a little bit deeper and use the fact that M2 to infinity is isomorphic to a tensor product of countably many copies of 2 by 2 matrices. And note, this implies that if I take M2 to infinity, and if I take tensor product of countably many copies of this, by the way, what does this mean? So you're taking finite tensor products, because algebra is unital, you have unital embeddings, so you have a natural directed system of algebras, you're just taking the inductive limit. Right? So infinite tensor product is just inductive limit of finite tensor subproducts. Well, this here, well, what is that? Well, each one of the factors here is tensor product of countably many copies of 2 by 2 matrices. All F0 times all F0 is all F0, right? So this is, you can just basically, oops, sorry, this is not what I wanted to write. You can reshuffle them, and this is just M2 to infinity. Right, so this is Liszt algebra, which is equal to tensor product of infinitely many copies of itself. And this fact is used in the following. So here it is, that if A is isomorphic to A tensor M2 to infinity, then A is an elementary submodel of A tensor M2 to infinity. Right, so again, as I mentioned, this is not necessarily true for certain Kirchberg algebras, so we do need something special about this algebra. Okay, so for that, let us just remember again what it means to be elementary submodel. So A is elementary submodel of B if A is a subalgebra of B, and moreover, if you take any formula, C of X bar, and for A bar, any tuple A bar in A, which has the appropriate sort, appropriate format as to be inserted in this formula in place of X bar. If we compute C at A bar in A, or if we compute it in B, we get the same value. Right. So in other words, these functionals that A and B induce on the Banach algebra of all formulas, they coincide. Okay, and here is the fundamental Tarsky-Watt test. I mentioned it before. So if A is subalgebra of B, then A is elementary submodel of B if and only if the following condition holds. For every formula phi, which has, you see, variables are grouped as X bar and Y, and for every A bar in A, which is of the same sort as X bar, we have the following. If you take infimum over all Y in A of phi at A bar Y, but computed in B. So you see, the left-hand side is something of a mix. So we are taking infimum over A, but computing what we get in B. Then this is less or equal than the infimum that we get if we take infimum Y over B and compute formula in B as well. I mean, equivalently, really, the other inequalities is immediate because you're taking infimum over bigger set. Of course, it's less or equal. So really, we are proving equality, but this is the interesting case. You see, if you can prove this, then by induction on complexity of the formula, we can prove the whole thing. Remember, formulas are defined as the smallest family of syntactic objects which satisfy certain closure properties, composition of continuous functions, taking quantifiers, which makes it very easy and very natural to prove theorems about all formulas by induction on that complexity. And once you know that this is what needs to be done, it is very straightforward. You just write the formula and write it. But okay, this is a great test for checking the elementarity. So this is what we want to do. Just one thing, you see, norm of Y is taken over the unit ball in both cases. That's basically because syntax works that way, right? So technically, we could be taking norm over any ball of C star algebra in any sort, in other words. But because C star algebra is so homogeneous, all that matters is really what happens in the unit ball. So one can just write it this way. Right. So back to the proof. Right, so I'm just assuming I'm not proving Tarsky-Watt test. So you see, instead of proving that A is elementary submodel of A tensor M2 to infinity, because we have this isomorphism, I can just replace A with A tensor M2 to infinity, and I just need to prove this. Now, what does this look like? Well, it is really even something apparently more complicated. I can replace M2 to infinity with countably many copies of M2 to infinity, right? So I want to prove that this holds. Oops, here. Tensor product of countably many copies of M2 to infinity, and yet another. So it's a lot of M2 infinities. Now let's take a look at what is going on here. So let me add a page here. Try to draw a picture. So we have A here. And now what else do we have? Well, we have A tensor M2 to infinity, then A tensor 2 copies of M2 to infinity, and so on. So all the way up to countably many. So this is A tensor M2 to infinity. This is A tensor M2 to infinity, tensor M2 to infinity, and so on. So this is the entire thing. And this is sitting inside this other algebra. Now there, let's just call this B. This is B. Now we can go vertically here. So this is B tensor M2 to infinity, and so on. Now, what is going on here? Let's just zoom out to see Tarsky what test. Well, we fix formula phi, and we fix a bar in A. Now, where is a bar? Well, it can be anywhere. Actually, I have to be precise here. We are fixing a bar in a tensor, countably many copies of the car algebra. So where is a bar? Well, you see, everything here is happening up to some epsilon, right? We are trying to prove inequality. So as so often in analysis, you proceed by saying, well, fix arbitrarily small epsilon, and then do something. Well, if you fix arbitrarily small epsilon, then you can actually assume that your a bar belongs to some finite level of this algebra here. That it actually belongs to a tensor M2 to infinity some number of times, right? But by just changing it a little bit, right? It doesn't change formula much. And now, if this infimum here is attained, it is attained by something, by some, let's call it, okay, yes, right. So let's call it Y. So Y is some element that belongs to who knows what. Well, you see, it again belongs to, it somehow, you can approximate Y as a finite sum of elementary tensors, again, by changing it a little bit. Now, where are those tensors going to be? Well, some of them belong to this algebra where a bar belongs. Some of them belong to these other algebras. But you see, all of these algebras look the same. You just have lots of copies of M2 to infinity. And then I can just find automorphism of my algebra, which remains this remaining copy of Y bar inside here, without actually changing the value of the formula, right? That's one of the basic facts, that if you have an automorphism of an algebra, then if automorphism fixes some of the parameters, the value of the formula at those parameters is unchanged, right? So by doing that, we can push Y inside and actually prove that this left-hand side is less or equal than right-hand side less than plus epsilon for any given epsilon. And then because epsilon is arbitrary, the conclusion follows, right? Okay, so far, we haven't done anything deep at all. So we didn't use any special properties of M2 to infinity. Okay, you can say, well, we use the fact that it's it's infinitely self-absorbing tensorially. Yeah, okay, we use that, but there is much more to this theorem than what we have seen so far. So proofs go through for every separable, I should say, nuclear. Okay, actually, I don't have to say nuclear. If I say A here, right, so all that matters is that A is separable, and all right, so we want it to be unital. But since M2 to infinity is nuclear, we don't need to worry about that. So let's see what have we proved so far. If A and C are separable, unital, and at least one of them is nuclear, right, that suffices to have these tensor products. Then if you write D to be tensor product of infinitely many copies of C, then we have that 1 implies 2 implies 3, and 2 implies 4. So if A is isomorphic to A tensor D, then A is elementary submodel of A tensor D. If A is elementary submodel, then D embeds into relative commutant. And also, if A is elementary submodel, then D embeds into relative commutant in the asymptotic sequence algebra. All right, so really the question is, how do we go back, right? Which is really the interesting thing, right? So it's really what is used in classification for these algebras and for others, that if something embeds into relative commutant and that something is sufficiently nice, so this is where we need some extra assumptions, then you can prove interesting results about those things. Right. So here is, let me just, before we proceed to do that, let's state an exercise. If D and A are separable and unital, then D embeds into relative commutant of A in the ultra power, if and only if D embeds into relative commutant in the asymptotic sequence algebra. So these two are actually equivalent. We haven't proved those because it's going to fall from something else, but you can just see. Okay, and another fact is that we do need to throw in an extra assumption. Basically, extra assumption is only additional property of the Car algebra, because there are separable and unital A and C, such that A is nuclear and A is elementary submodel of tensor product of countably many copies of C, but A is not isomorphic to A. There is a tensor missing here, to A tensor product of countably many copies of C. I'm not saying this is an exercise because the proof uses something that I haven't mentioned. A very nice fact due to Kirchberg, that if you take C-star algebra, then ultra power is almost never nuclear. The only situation in which ultra power is nuclear is if your algebra is what is called subhomogeneous, namely if it can be, okay, so how, basically if it's product, if it's a subalgebra of product of many copies of some fixed matrix algebra. So only in that situation, the ultra power is nuclear. In particular, if you have a separable infinite dimensional C-star algebra, its ultra power is not going to be nuclear. So if you take that as a black box, then this is an exercise. Okay, so now we're getting serious. And here's the property of M2 to infinity, which we need in the upcoming proof. Look at M2 to infinity tensor M2 to infinity. This algebra has a very natural automorphism, which is the flip, right? So we just send A tensor B to B tensor A. Right, so just flipping the two coordinates of the tensor product. That automorphism is what is called approximately inner. Now, what that means, it means that there is a sequence of unitaries in our algebra, such that if you look at conjugation by those unitaries, we have a sequence of automorphisms. That sequence of automorphisms happens to converge pointwise in point norm topology to an automorphism, and actually automorphism is the flip. Excuse me, automorphism. C-star algebras, if you have this property, are said to have an approximately inner flip. Now, okay, before I say about examples, why does M2 to infinity have approximately inner flip? Well, actually, the proof is very similar. The picture is very similar to our previous proof of elementarity. A tensor M2 to infinity is elementary submodel of A tensor M2 to infinity, tensor M2 to infinity. The key point in the proof is the following. Oops. Okay, I still haven't learned what exactly to press. Fine. The key point. The key point is the following. Every automorphism of Mn of C is inner. Right. This is just linear algebra. Right. So what is automorphism of N by N matrices? Well, it's really a unitary in a Hilbert space. I mean, conjugation by unitary in Hilbert space. So the only tiny wrinkle here is that unitary is not uniquely determined. It's uniquely determined up to multiplication by a scalar. You just need to pick a scalar and reconstruct the unitary. So every automorphism is inner, And now, again, if you look at the flip automorphism, all that matters, you see, this converges pointwise to the flip. Well, all that you need to make sure is that this converges pointwise to the flip to those algebras M2 to N. So let me write it down. M2 to infinity. Okay, you can write it as a tensor product of countably many copies of 2 by 2 matrices, but you can also write it as a direct limit of algebras of the form M2 to N. We might write it M2 to N to avoid confusion with that N over there, right? So just bigger and bigger matrices. So the elements which belong to these form a dense subset. So if you look at M2 to infinity tensor M2 to infinity, inside it, you have 2 to M by 2 to M matrices cross 2 to M by 2 to M matrices. The flip on those is inner because those are just 2 to M plus 1 matrices. Right, so you just have this very natural sequence of unitaries which implements the automorphism. Right, now I should say that there are many other important algebras that have approximately inner flip. So every UHF algebras are just tensor products of full matrix algebras. Also, the notorious Yang-Su algebra Z, I didn't say anything about it in this course, but if you take pretty much any other course that talks about cyst algebras, you'll hear a lot about it. It's a fascinating object. Also, Kirchberg algebras O2 and O infinity. I mentioned a little bit about O infinity a couple of classes ago, and many other cyst algebras. Now, this is okay, fine. So these are interesting facts. But what is really remarkable is a theorem of Efros and Rosenberg, who proved that having approximately inner flip actually has very strong consequences to the structure of that cyst algebra. So if you have cyst algebra which has approximately inner flip, then it has to be simple. It can have at most one tracial state. And finally, it has to be nuclear. So it's really remarkable assumption on algebras. And you know, it's really basically, to me at least, one of the main contributions of Efros and Rosenberg was isolating this key property and seeing how important it is. All right. So, okay, right. So here we are. So proof that if this car algebra embeds into relative commutant of A in its ultra power, or pretty much the same proof in the asymptotic sequence algebra, that this implies that A is isomorphic to A tensor M2 to infinity. Really, you know, the real theorem is that if D has the approximately inner flip and D embeds into relative commutant of A in the ultra power, then A is isomorphic to A tensor D. Then A absorbs D tensorially. So what is the trick here? Well, it's really, the point is here really theorem that comes from cyst algebras, but it has really this general model theoretic flavor. So okay, let me say what the theorem is, and then I'll say why I think so. So if you have A and B, A is a subalgebra of B, it's separable, and there is a sequence of unitaries in the ultra power with the following property. It has the property that if you look at conjugation by these unitaries, pointwise on A, those automorphisms converge to the identity. And the second property is that, again, if you look at this conjugation by these unitaries, on B, so for each element of B, they don't converge pointwise, but that element approaches A. The image of that element approaches A more and more. Then A and B are isomorphic. You see what is going on here. You see the assumption is something about alpha power. Now, the only specific part of this theorem that's really specific to C algebras is that we are talking about unitary. So it's really some notion of inner automorphism. And you see, there is a fact that if you have unitary U, so if U is a unitary, then U has a representing sequence. Oops. Sorry about this. What? Okay. Presenting sequence, let's call it UN, such that each UN is unitary. Okay, so the reason for this is the following. The relations x star minus 1 and x star x minus 1, which are really the defining relations for unitaries, right? So if x is a unitary, if actually I'll just say the relation and put these under maximum sign. Right, so this relation, this being equal to z, I have to be careful where I'm writing, equal to 0 is what is called weakly stable, or no, that will be for C algebra, is for model theories definable. What that means is, okay, let me just call this Rx so that I don't have to write it. So what this means is that for every epsilon greater than 0, there exists delta greater than 0, such that for every A and for every A in A, if R of A as computed in A is less than delta, then there exists A in A such that R, there exists B in A such that R of B is equal to 0, and the distance from A to B is less than epsilon. All right, so in other words, if you have something in A, the only possible reason why it can have a small value of R is if it is close to the 0 set of R. Now, this is equivalent. So this weak stability is equivalent to saying that the ultra power of R is equal to R of the ultra power. That for every A in the ultra power, R of A is 0, if and only if A can be written as representing sequence modulo ultra filter, so that the ultra, oops, this is at A is 0 for all n. I should say this is not automatic. For example, if you write formulas that describe when an element is normal, that is not weakly stable. So you can have in the ultra power some element which is normal, but there is no way that you can represent a sequence consisting of normal elements. Right. Okay. So I just made a digression. So this is weakly stable, and now because of that, you can choose a sequence of unitaries. Now, why are we doing that? Well, you see the sequence of unitaries. These are unitaries in the ultra power of B. They define you these maps between A and B, and now there is an so-called intertwining argument. If you look at those unitaries, once you lift them, so you see we already had a sequence of unitaries, UN, but now we lift each of the UNs to a sequence of unitaries, but this time unitaries in B. And what those unitaries give us, well, if you have A and B, they give you embedding. So first, there is natural embedding of A into B. A is a subalgebra of B. But now you have a map from B to A, and then again map from A to B, and so on. And these maps don't commute with, these are on a horizontal, I have identity maps. They don't commute exactly, but they commute approximately. So in the limit, you get a map and you actually get an isomorphism out of here. So I'm obviously not giving you details, but this is a special case of Elliott's intertwining argument. And anyways, so it gives that under these assumptions, let me just go back to this. So under these assumptions, that A is isomorphic to B. Now, the point is that if D is strongly self-absorbing, sorry, I was talking about approximate linear half-flip. If D has approximate linear half-flip, then we can choose such a sequence of unitaries. So let me say, any questions? Okay, let me just say more about that. Maybe I should change color to something more reasonable. So suppose that D embeds into the relative commutant. Okay, now what do we get out of here? Well, this was discussed before. You see, what this really means is that certain type which describes D as sitting in the relative commutant is consistent with A. And now, because we can take a bigger separable elementary submodel, which contains D and A, type is consistent over that element as well. So we can embed not just D, but we can embed D into its relative commutant, and then another copy of D, and another, and so on. And what we get by countable saturation is that a tensor product of countably many copies of D embeds into relative commutant, right? So basically, along the way, we also scooped the other, well, to some extent, the other equivalences with M2, right? So even if you just know that M2 embeds into relative commutant, you can get it, the car algebra embeds into relative commutant, which is what we want, right? So then this embeds. Now, what do we have now? Now we take, okay, A is A, and take B to be A tensor this. Now, what do we have? Well, here is A. Here is B. And now they are both sitting inside the ultra power of B. And what, oops. So here we have this copy of D. Now note that by the part of the theory that we proved so far, the tensor product of infinitely many copies of B embeds into the relative commutant of B in its ultra power, right? Because B absorbs the tensorial. So we have here another copy of D. Let's call this D0 and D1, right? So D0 is isomorphic to D1, is isomorphic to D. And now what do we have here? Well, we have these approximate linear flips. So we have unitaries which implement flip between these two. And let me see, so there was a subtle point here. Oh yes, right. Yeah, okay, all right. So you see what we have. Not only that this, okay, we already know this. Here is B, but even in the ultra power of A, and this is actually the copy of D that I want. Let's call it D2. Now that I started naming different copies of D. So there is also D2, which is isomorphic to this, and D2 embeds into relative commutant of A in its ultra power. Right? And now we have, I'm not even sure I'll need this copy, maybe I just don't need it. So you see, we have approximately a flip between these two copies. Right, so actually I don't need this copy. This was not needed. Right, so we have approximately inner flip. Right, so we have these unitaries which implement the flip. Now, what are those unitaries doing? Well, they move elements of B. They don't move A. Right, so note that both D0 and D2 are subsets of the relative commutant. Right, they're all commuting with A. So the flip also, flip belongs to this algebra generated by those two, because they are nuclear. This is actually, they're nuclear and simple. This is really a tensor product of those two. So we have those unitaries, and they, you see, what is D2? Well, D2 is sub algebra of the ultra power of A. So if you take those unitaries, which represent these approximately a flip, and leave them, find representing sequences, each element of D2 is really represented by a sequence of elements of A. So each one of these unitaries presents unitary that sends B into A, closer and closer to A. And by just diagonalizing, right, at this point, we have countably many sequences of unitaries. Because A and B are separable, one can diagonalize and choose a single sequence of unitaries, which does exactly what we want to do. And out of that sequence, now you just use intertwining argument and get that A and B are equivalent. Any questions? Okay, so you see, this is the case of the alpha powers, but in case of the asymptotic sequence algebras, you see, I didn't use that much of elementarity, actually exactly as much as it was used for the embedding theorem it is used here. So literally the same proof works for the asymptotic sequence algebra, completely unchanged. Now, what is notable here, remember last time I sketched this proof of the reindexing argument, which is often used in combination with this, which doesn't work for the alpha powers. So let me just see if I wanted to say something before I move to that, or yeah. So that's pretty much that. So I'll just move to the very last topic. So because of this reindexing, there is this fact known that alpha powers and asymptotic sequence algebras can be used interchangeably, and it's not quite clear exactly why one of them is more convenient sometimes and sometimes is the other one. So here is a result which somehow helps make them more interchangeable. So if you assume the continuum hypothesis, then there is a non-principal ultra filter on the natural numbers, such that for every separable algebra A, this quotient map from the asymptotic sequence algebra to the ultra power has a right inverse. Now, remember, asymptotic sequence algebra is L infinity of A modulo C0 of A. The ultra power is L infinity of A modulo Cu of A. This ideal is much bigger. So Cu of A includes C0 of A. So there is natural quotient map here, Pu. And A embeds diagonally. Let's call this iota infinity. This is iota U into each one of these two algebras. Right, so arguments sometimes take place in relative commutant inside asymptotic sequence algebra, sometimes in relative commutant inside the ultra power, and there is this natural quotient map, but there is no obvious map that goes back. Little argument using elementarity saturation shows that whatever embeds into relative commutant of U embeds into relative commutant of the asymptotic sequence algebra, but that's not powerful enough to explain everything. So what happens is that under continuum hypothesis, you can choose an ultra filter. This doesn't work for every ultra filter. You actually have to choose it carefully. So that this map here has the right inverse. And now what that implies is that literally you can just move from one to the other with these embeddings. If you're embedding simple Cist algebras, they're going to be unchanged after these maps. And you have that. So I'd like to say a few things about how this is proved. It's not very long proof, but I just don't have much time left here. So I'll just say a few words. So before I say about the proof, let me just say this. You see, this result is supposed to explain why these algebras are interchangeable, but of course, in classification, you never hear the assumption of continuum hypothesis, and you don't want to hear it. Those are supposed to be theorems in ZFC. Well, indeed, the fact is that all the relevant consequences for classification are absolute for transitive models of ZFC. Now, what that really means is that if you want to prove one of those, you can just call a set theorist to collapse continuum to Aleph 1 for you, without basically force continuum hypothesis. And then you can apply this theorem and then just go back to your model and say, well, but I didn't change the truth of these statements, that they're still true here. So basically, this is an example in how theorem proved using continuum hypothesis, and all kind of ultrafilter doesn't even exist, means that ZFC can be useful to prove ZFC results. That's one of my favorite topics. But let me say just a little bit more about the proof of this. So the key point is this here. So for every separable C-star algebra, if you look at the algebra C of K, that's continuous functions on the Cantor space. And tensor A with continuous functions on Cantor space, then you can embed this elementarily into A to infinity, into the asymptotic sequence algebra, in such a way that the embedding commutes with diagonal embedding on A. So what that means is the following: this A tensor C of K, which is, by the way, isomorphic to continuous functions from Cantor space into C-star algebra A. Right. So this is elementary in A infinity. Now, what did we learn about elementary submodels? Separable elementary submodels in continuum hypothesis. If you take alpha power of this, this is countably saturated elementary extension of this algebra, which is under continuum hypothesis of density Aleph1. And with continuum hypothesis, both of these C-star algebras are elementarily equivalent and saturated, and therefore they're isomorphic, right? And moreover, isomorphism can be assured to preserve this diagonal copy of A. So what this really means is that for all practical purposes, the asymptotic sequence algebra actually is an ultra power. It is just not ultra power of A itself. It is the ultra power of A tensored with continuous functions on Cantor space. I should probably say why, how do you embed continuous functions on Cantor space into A infinity? Well, let's just, let me just see how this works. Right, so this is what we want, to embed it unitally, again, all embeddings today are unital, into this relative commutant. Well, it is slightly easier, but basically the same, just to see how C of K embeds into L infinity. So what are continuous functions on K? Well, again, just like earlier on with Carl algebra, we can think of these as an inductive limit. So what is Cantor's set? You can think of Cantor's set as an inverse limit of finite metric spaces. Just take space with 1 point, and then space of 2 points, which both points map onto it. And then in the next level, you have 4 points, so it's 2 map to this. So what is C of K? Now, if you take the functor which sends spaces to C-star algebras, it's contravariant. So C of K is just isomorphic to the direct limit of what? Continuous functions with finite spaces, which are just finite powers of complex numbers. So this is really C to 2 to N. Now, when I write it this way, what I mean is every time we split each of the points, right? So at the nth level, you have 2 to N points, you just split each one of them, and you're just embedding. Actually, embedding really has essentially the same formula that the embedding between those matrix algebras had. You're just embedding in diagonal, just duplicating all the entries. So anyway, so it looks like this. So how do you embed C of K? Well, you just embed complex numbers into L infinity. How do I do it? sorry, L infinity mod C0. That's what I wanted to say. C looks like complex numbers, which is not supposed to do. Well, for the first level, just choose two infinite sets, right? And one copy of complex numbers goes to one, second to the second. In the next level, you just split each one of those two infinite sets into infinite sets and just send them and just continue splitting. So at any point in the nth step of your induction, you have two 2n disjoint sets whose union is everything. You just split each one of them into two infinite sets, and that gives you embedding of these continuous functions of this dense subalgebra of C of k, and then just take completion. And that embedding is elementary. And the proof again uses Tarsky test and a few tricks. It's really reasonably simple proof, but it goes some way. So any questions? Okay, so now what is a punchline of sorts here? But remember, what we are trying to do is somehow find this the right inverse of the quotient map from the asymptotic sequence algebra to ultra power. Now, what do we have? So consider the following structure. Now this is something that we haven't done yet in this course, but it is used in models theory quite often and quite efficiently, that you somehow conflate more than one model together into a single model. And think of it as sort of a multi-sorted structure. So what do we do here? Well, we look at a tensor C of k, comma a, and now we look at projection map P0. So I'll tell you what in a second what P0 is. So well, fix a point in the Cantor set. I can call it 0, right? They're all the same. There is a homeomorphism which sends any point of Cantor set to any other point. And just what is P0 of a tensor C of k that sends this to a. Well, you see, just think of this as continuous functions from k into a. And what is P0? P0 function f, it's just the evaluation. Right? This is a star homomorphism. I'm simply evaluating function at that point. And now this here is a quotient map. That quotient map has the right inverse. What is right inverse? Phi sends a to continuous functions from k to a. Simply phi of a sends a to the constant function. Right, so it sends it to function f, such that f of x is equal to a for every x in the Cantor set. This is again a star homomorphism. And this is my structure. So you see, this consists of two C-star algebras and two maps between them. Okay, so here it is. Right, so you have P0 going down and this phi going up. And indeed, phi is the right inverse. If I compute P0 composed with phi, it is indeed identity on A. Right? If I apply phi first, go up, go down. The other way around, it's not, but this is all we need. Now, the point here is that this structure here what we do is we take an alpha power of this structure. So taking alpha power, what do we get? Well, if you take an alpha power, you get something that looks like your algebra. Well, downstairs we get U. What do we get upstairs? Well, if you assume continuum hypothesis, then this alpha power will be isomorphic to the asymptotic sequence algebra because you have this elementary embedding. What is the alpha power of the quotient map? Well, the quotient map. What is the alpha power of this? Well, it's something. Now, the problem here, you see, if it was as simple as I just said, I wouldn't have the need to say that we need to choose ultrafilter carefully. So what is the point here? Well, I actually need this this alpha power. It's not obvious that it is countably saturated. So here is the fact that this alpha power here is countably saturated if and only if U is what is called a P point. Now, what this means is the following. If you have a sequence of sets in U, countable sequence of sets in U, then there exists another set in U such that it's included in each x of n modulo finite. So this difference is finite for all n. So if you want to think topologically, it means that if you take any countably many open neighborhoods of your point in beta n minus n, then if you intersect them, you still have something that is a neighborhood of your point. So countable saturation falls from this being a P point. And now if U is a P point, then indeed this structure is isomorphic to exactly what you want it to be isomorphic to, and it gives you this right inverse to the map. Now, here is the reference. So it's paper is on the archive. And yeah, so I guess it's probably a good idea to leave some time for the questions, because as I said, this is basically the last, technically, the last real class. So yeah, that's all. Thank you. And yeah, let me know if you have any questions.
Can you, I have a question, Ilijas.
Yes,
Can
sure.
you say a bit more about the role of the P point on that proof? I mean, why is a P point?
Yes, I can. So you see, the point is that okay, it is you know, it depends on a few things that I haven't said anything about. So actually, to say it, I just have to remind you first, how do you prove that alpha power is countably saturated? So the proof it uses Walsh's theorem very substantially. You see, because you have approximate realizations of finite subsets of your type. You have countably many of them, and need somehow to chop them up, to put them up into L infinity of A, and make sure that by looking at finite segments of those bits, you know that they're going to satisfy this. So that's Wash. Now, why is A infinity countably saturated? Right, so I didn't prove this. I just said that what this uses is this Pfefferman-Watt-Ghassemi theorem that enables you to do the same thing. You have, so I'll say Pfefferman, Watt, and Said. That again, but by just knowing finite pieces of your represented sequence, you can figure out what formulas it satisfies. So we can still chop up those elements and put them together, assemble them at the end, and make sure that they realize the given type, required type in the ultra power. Now we want to do the same in our structure. Now, what is our structure? Well, you see, it has this. What is the structure? The structure is the ultra power of C of Ka and Au. Sorry. Oh, okay. Yeah, actually, good that you asked, because what I said, this is countable. Sorry. Actually, it's very good that you asked. I just said something else. Thank you, Daniel. So basically, this is countably saturated, but it's really this part here that is critical. A infinity Au and this. It is really the question whether this is countably saturated, because any ultra power is countably saturated. I said something very silly here. So of course this is countably saturated, but the point is that we want to make this isomorphic to not just to CKA, but to the entire thing, and then the isomorphism sends phi to the right inverse of this map PU. How do we do that? Well, you see, A infinity, AU, PU, countably saturated. Well, you need some sort of Pfefferman-Watt-Ghassemi again for this. Oops. And that's fine. That theorem is not difficult to prove, but it's really this chopping up finite pieces of your realization and putting it together that is problematic. You see, if your ultra filter is not a P point, then you don't have a place to start. Because again, how do you prove countable saturation? You have countably many formulas with countably many parameters in your algebras. Now, for each one of those formulas, you have infinite subsets of the index set at which they have certain values. Actually, in the case of Pfefferman-Watt-Ghassemi, for every formula, to compute that formula in the structure up to any given epsilon, you have a finite set of different formulas. You have to compute that in the structure, in the original structure, and basically estimate them up to some epsilon. So you have these countably many formulas, and now some of them, what is going on? You have L infinity of A, and you have these formulas Cj of X bar for J in N that somehow control your type. Right? So your type is determined by those, and you have parameters in those formulas. So now for each one of these parameters, you have to see when is this greater than epsilon or less than epsilon, something like that, and you get certain sets. But now it matters when are those sets in the ultra filter, where they're not in the ultra filter. So you have countably many sets that are relevant here. And some of them are in the ultrafilter. If your ultrafilter is a p-point, you can just choose a single set that is included in all of them, modulo finite. And what you have is, you have that set, X in the ultrafilter, and you have this complement which is not in the ultrafilter. And now you know that everything that happens here, you'll have dichotomy. So either set is infinite or it's finite. You don't have to worry about assuring that anything is in the ultrafilter. And then you can just proceed with the usual proof, just building up your realization from finite pieces and not worrying whether the right thing is going to end up in the ultrafilter.
Thanks, Ilijas.
Welcome. Any other questions? Well, okay, so I guess if there are no questions, then I hope to see you on Friday. Right, so we have presentations then, and I mean, as you can see, I skipped many details here and there, but I'll be happy to talk about those details if needed. And yeah, so see you on Friday, and have a great day. Okay.